Higher Notes 1.2 Forces. This is part 3, where we look at the application of Newton's second law to tension problems. So let's begin just by considering what tension actually is. So if we imagine two people and they're standing a few meters apart and they're holding a rope which is slack, like that. Well, if the rope is slack, what that means is that person A is not pulling on person B with a force, and he certainly can't push with a non-rigid object like a rope anyway. But because the rope is slack, person A is not pulling on person B. So there's no force being transmitted through the rope, and we say that the rope is slack. Another way of saying that is that there is no tension in the rope. Okay. Right. Now consider the same situation. But this time we're going to pull on the rope. In such a way that it becomes stretched and taut, T-A-U-T. Well, person A, let's say, does the pulling. Person B doesn't need to actively pull, he just holds the rope steady. He doesn't let it move one way or the other. But if person A pulls on person B, then he's exerting a force towards himself that way. And that force is acting through the rope, and it's the force that's making the rope taut. And we call that force a tension T. So person B would feel a force, he'd feel his hand being pulled, and you'll see this in the lab. He would feel that tension T. Now, at the same time, person A would feel person B resisting the pull, so to speak, and what you find happens is that there's an equal and opposite tension force acting through the rope. I'll call it T dash, acting in the other direction. So when person A pulls person B feels that tension force T. But person A feels a resistance to his pull. He feels person B pulling back on him, even though person B isn't actively pulling. He could be a fixed wall, for example. And T dash then is what person A feels. Okay. Now effectively what we've got here is T being an action force from Newton's first law, and T dash being a reaction force. So notice that tension T acts on body B, the right hand person, whereas T dash acts on body A, the initiator of the force. And the rope is taut, or we say under tension, meaning the same thing. Whenever a rope is taut, you always have tension acting in opposite directions at each end. It's impossible to have the tension acting only in one direction, otherwise Newton's third law would be broken. So T equals tension force, and basically tension is simply a force acting through a string, rope, wire, or a metal bar. Metal bars can carry tension. For example, in a car pulling a caravan, they're effectively linked by the tow bar and coupling, and that is a metal bar connection. Okay. The force is a force like any other force, so it's measured in newtons, and its symbol is T. So that's what tension actually is. It's just a force acting through a rope. The kind of problems you need to deal with tend to involve cars pulling caravans, and there's tension between them in the coupling, dogs pulling sleds, tractors pulling trailers, that kind of thing. But they can all be summarized in this generic description I'm about to give you. So here's the situation diagram. And we'll have typically two bodies, which I'm just going to represent as rectangles. They needn't be the same size, so I'll try and make one of them look a bit bigger. Okay. Don't know if I can move that up a bit. Not to worry. They're both sitting on the bench anyway. And they will be linked by some sort of rope which couples them together. Okay. Now, typically, there will be some sort of applied force which is exerted directly on one of the blocks. In this one, it's the right-hand block. So we'll call that F applied. Let's make it 100 newtons. Let's make M1 be 0.2 kilograms. And let's make mass 2, the bigger one, be 0.6 kilograms. Let us have frictional forces on each one. So we'll call frictional force F1 be 10 newtons on the small block, and we'll have frictional force F2 be 20 newtons on the bigger one. So you can see the situation looks fairly involved, and this of course is the rope which couples the two blocks. When two bodies are joined together physically like this, we say that they're coupled. They're joined by a rope or equivalent. So what this basically boils down to is that if the overall force on the whole system to the right is bigger than the overall force on the whole system to the left, then the whole system will accelerate to the right. Okay, so that's the situation diagram. I'm now going to redraw it as a free body diagram. It will look quite similar, but it's just a little bit simpler. So we have our two blocks. like so. And now we can put in the various forces. So we've got our applied force, so someone's pulling the blocks along with 100 newtons out there. Obviously they're coupled, so there's our rope. Now as soon as we put the rope in, we can immediately enter our tension forces T and T dash. Now these two forces don't balance each other, although they're equal and opposite. They're a Newton 3 pair, so they're acting on different bodies, and two forces acting on different bodies can't balance each other. You can only have two forces balancing if they act on the same body. So we've got our friction, which we need to put in. So we'll call that friction 1. What did we say that was? 10 newtons. And we've got friction 2, which is 20 newtons. Now, an important bit of analysis here. You should always, when you're sketching this, and I do recommend you sketch this diagram, draw a dotted line around the whole block system, because that dotted line encompasses what we call the system. In physics, a system just means a collection of bodies which are linked together in some way. So you could break up a system into individual parts. Now just observe one thing here before we proceed. The applied force of 100 newtons can be thought of as applied to the entire system. The two frictional forces can also be thought of as applying to the whole system, because they both oppose the motion of one of the blocks, therefore they oppose the motion of the system. But the two tension forces are very much internal, as we shall see. Okay, this will become clear when we do an example. Okay, so let's imagine then that the whole system is indeed accelerating to the right, and you can show that outside the dotted line with a double-headed arrow. Keep it outside the dotted line so you don't get it mixed up with a force, and the double-headed arrow shows it's an acceleration. So here is the typical question then. Two things. Find A, the acceleration of the smaller block, and B, the tension in the coupling. Right, that's our two standard sorts of question. Just checking the mass, 0.2 and 0.6. Might want to put that in. Just so we don't get them mixed up. Right, so let's do the solution. We'll begin with part A. Well, we're interested in the acceleration of the smaller block. And the first thing to notice is, because they're coupled, they're like two railway carriages. They must have identical motions because they're coupled. So if you think of a train with various carriages, if the train's accelerating, every carriage is accelerating. If the train's going with uniform velocity, every carriage goes with that uniform velocity, and so on and so forth. So if we can get the acceleration of the system, and I'm going to put a little s in now to A there to show it's the acceleration of the system, Then we've got the acceleration of each of the individual blocks. So if you're ever asked for the acceleration of one of the component blocks, just get the acceleration of the system and you've got it. So we're going to work with the system. So put a little subheading, system, and that just lets the marker know you're dealing with the whole system. Right, well, it's a bit like some of the earlier problems. There are two stages in the solution, and stage one is basically sorting out what the unbalanced force is. Well, you basically take all the forces to the right and you take away from them all the forces to the left. So we can set up an equation for that. It's the applied force, take away friction 1, take away friction 2. Well, we said the applied force was 100 newtons. Friction 1 we said was 10 newtons. And friction 2 was 20. So it's 100 minus 30, 70 newtons, and that's obviously to the right. Direction is important. We generally don't need the sign convention here because there's usually only one direction involved. It'll either be right or left. Stage 2, well, having got the unbalanced force, we can now apply Newton's second law, which is the real focus in this section. So we always begin, as always, with F equals ME. Now, because we're dealing with the system here, remember, I'm going to put MS for mass of system and AS for acceleration of system. Well, the mass of the system in total is the 0.2 kilogram mass added to the 0.6, so that's 0.8. And the acceleration is the unknown. And we now know that the unbalanced force is 70 to the right. So the acceleration of the system then is 70 over 0.8. And when you do that, 70 divided by 0.8, you'll get 87.5. I'm just going to round that up to two significant figures, 88 meters seconds to the minus 2. That's a pretty big acceleration actually. And that's to the right. And there's our answer then. That's the acceleration of the system. Now we're not quite finished because the question actually said, what's the acceleration of the smaller block? So to finish off, so the smaller block will also accelerate at 88 meters seconds minus 2 to the right. Okay, because it's part of the whole system and they all accelerate at the same rate. The only reason that's such a big acceleration, of course, is that 100 newtons with friction of 30 leaves 70 newtons, which is really, 70 newtons is quite a big force on a small mass like that. Right, so there's our system and blocks accelerating. Second part, what's the tension in the coupling? Now, whenever you're asked for the tension in the coupling, you're not dealing with the whole system, because the whole system is the two blocks together all moving. To get into the tension, you always need to draw a free body diagram for one of the blocks only. So you've only got one unknown tension. It could be either of them, but very often choosing one of the blocks at the end, usually the tail end, is slightly easier. Not always, but very often. So to answer B, I'm going to draw the small block and all the forces on it. So it's a free body diagram for the small block to get the tension. You'll see how this works now. So draw free body diagram for small block. Well, you'll see why I'm doing this now. So there's my block. Now it's a free body diagram, so I want to put in all the forces acting on this block. Well, if you look carefully, there are only two forces acting on the 0.2 kilogram block. There's the tension force T to the right, and there's the frictional force F1, 10 newtons, to the left. Remember, T dash is acting on the 0.6 kilogram block, not on the 0.2, so we don't show that. And the 20 newton friction is on this 0.6 as well, so that's what we've got. Right, so we've got T to the right, tension. Now that's our unknown. This is our 0.2. And we've got our frictional force, small force, 10 newtons to the left. Now don't forget, we've just established that this is accelerating to the right at the 88 meters seconds to the minus 2. So this problem has boiled down to a single body with two forces on it, with a known acceleration, and one of the forces is unknown. So we, as always, we apply Newton's second law. Now you could do a separate calculation for unbalanced stage 1, stage 2 again, but sometimes with these simple ones it's easy just to insert it into this equation, and by that I mean we can say that the tension to the right, take away the small friction, that's actually F1 to the left equals MA. Tension is our unknown, put in the numbers then. That's our 88. So using our calculators, 0.2 times 88 gives me 17.6. Bring that minus 10 over and it goes there. So the tension equals 27.6 newtons. So that's the tension in the rope, which would allow that system to accelerate to the right at 88 meters seconds to the minus 2. Now I could have chosen the right-hand lock, and I would have set up a similar equation, 100 newtons to the right. My opposing forces to the left this time would have been T dash plus 20, because they both oppose the motion. The acceleration would have been the same, 88, and if I'd worked that one through, I should have found that T dash would also equal the figure I've just got. That's the 27.6 newtons. So that's how you apply Newton's second law to tension problems with